Alright, hi everyone, welcome to my YouTube channel City of Electrons. So in this video we are going to talk about this transistor model. We really need this. In my last video we talked about this, like introduction to small signal analysis. Okay, small signal analysis, AC analysis. So in this video we are going to talk about the transistor model, because in terms of small signal analysis we need this model. Why do we need it? First of all, what is a model? So a model is a combination of circuit elements that best approximates the actual behavior of a semiconductor device under specific operation. So if you want to hear the name model, just think of equivalent circuits. Okay, equivalent circuit. So it allows us to apply basic methods of circuit analysis to determine the response, which is output of the circuit. Okay, so just a few things to bear in mind, or a few things to note, is that transistor models are most frequently used to represent transistor in sinusoidal AC domain. So when we have a transistor like this, the model will represent it in a form or in an equivalent circuit where we can apply basic circuit analysis techniques, okay, like KVL, KCL, and then voltage divider, current divider rules, things like that. Okay, so we said one of the key things to note is that transistor models are most frequently used to represent transistors in sinusoidal AC domain. So while we have this in kind of DC domain, we use the model to represent it in AC domain. Okay. Then the next thing to note is that the magnitude of the input signal will determine whether small signal or large signal analysis will be applied. But of course, this series now we're talking about small signal analysis. This second point just points out that what comes into the system, the input signal, will determine whether we use a small or large signal analysis. And then the third thing to note is that the key to transistor small signal analysis is the use of equivalent circuits. That's models. Okay, so using models is kind of the key to analyzing small signal. Okay, then the next thing to note is that the special voltage and current, the specific voltage and current at which the transistor operates is biased to operate, okay, is known as operating point. This is one keyword we have to bear in mind, operating point, which some call Q point. Okay, so it is that point where a specific voltage and current is set where the transistor begins to operate. That specific voltage and current is known as the operating point. Okay, where the is biased to operate. Okay, don't worry if you can't really recall all these points. As we go on, you understand the value of these key points, or these things we said we are talking about now that we should note. Okay, so then the next thing is models parameter. Once you hear this thing, a models parameter, what they mean? They refer to specific values of elements within the equivalent circuit, e.g. resistance value, current value, voltage value, and capacitance value. Okay, so when we write this circuit, this in equivalent circuits, that's in the AC domain, there are parameters. So those parameters, they are known as model parameter, the parameter of the model. But when we say parameter, we are not talking about something strange. We are talking about something we are already familiar with. That's resistance value, current value, voltage value, and capacitance value. Then the last point to note here is the DC current, which is IE, and the DC emitter current, which is IE. It determines the AC level of resistance of diode. Okay, it determines the AC level. Now, RE equals 26 millivolts divided by IE. So this IE will determine the AC resistance of the diode. Okay, like I said, in case all these things we are talking about, all these points, they don't really appear useful or meaningful now. Don't worry, just relax. As we continue in this series, you begin to see why we said these things are important to note. Okay, so those are the key points to note in terms of transistor models. So for transistor models, there are two common models or two approach to equivalent circuits. One is the RE model and the other is the hybrid parameter equivalent circuit. Okay, so we'll be working with the RE model, but let me just say something about the hybrid parameter model. So for the hybrid parameter model, the parameters of the model for a specific operating point is provided by manufacturers. See, this is kind of the key thing to note. Okay, this is kind of the key thing to note for hybrid model. This is kind of the key thing to note. So, and one thing here is provided by manufacturers. And remember, we said something about operating points. Okay, so parameters of the model. Remember parameters, we said parameters, models parameter, they are resistance value, current value, and so on, of the equivalent circuit. Okay, so when we take the equivalent circuit of this guy to the AC domain, the parameters there, which means the voltage parameters, okay, models parameter, resistance, current, voltage, all those things, they will be determined by the manufacturer. Recall, the parameter of the model for a specific operating point. What did we say about operating points? Come back to this key point here. We said for operating point, it is a specific voltage and current at which transistor operates. Okay, so where a specific voltage and current where transistor begin to operate, that's the operating point. Okay, that's your operating point. So the specific operating points, those parameters for a specific operating point, those parameters, they are given by manufacturers. That's for the hybrid parameter. Okay, that's the main point for hybrid parameter. But for hybrid parameter model, but for the RE model, the parameters of the model are derived directly from the operating point. Okay, so parameters, of course, that means the voltage, current, resistance value of the operating point. Okay, of the operating, sorry, the for the RE model, the parameters, which are voltage, resistance, current, those values in the equivalent circuit, those values, they are derived directly from the operating point, not from manufacturers. Okay, so for RE model, we get it from operating points. So what is the voltage and current where the transistor begin to operate? We derive the parameters from that. That's for RE model. But for hybrid parameter model, at a particular operating point, voltage and current where the transistor begin to operate, we get the parameters from manufacturers. Okay, this is kind of the major difference between the hybrid parameter model and the RE parameter model. Now let's just talk about this stuff here in the hybrid parameter model. You say if the operating point changes, recall that we get the parameters for an operating point from manufacturers. That means if the operating point changes, you need to consult the specification sheet again to get the new parameters. Okay, now this is kind of the idea here. Let's say this is the operating point. Okay, this is your operating point, and for each operating point we have the parameter for the operating point. We have the parameter for the operating point. We have the parameter for the operating point. Okay, so if the operating point change, and we got this parameter from manufacturers. So if this operating point changes, we need to go and look at the specification sheet to get the new set of parameters. Okay, of course, it's provided by the manufacturer. This specification sheet is provided by the manufacturer, so you have to go and look at it. Each time the operating point changes, you have to go and look at this. Okay, now this process needs to be repeated. That means the process of checking this again, checking the specification again, that process will have to be repeated for each new operating point. Well, this is useful when high accuracy is required. Okay, but for RE model, since we get our parameters directly from the operating points, okay, now check this out. If the operating point changes, there is no need to consult specification sheet for new parameters. Now this makes the RE model flexible and convenient. Okay, so no need to go and check and check and check, like check and check. No need. Just derive once the operating point changes. No problem. Just derive the new parameters directly from the operating point. That's for RE model, and that makes it flexible and convenient to work with. And that's what we are going to be dealing with. Okay. So now, how do you obtain the AC equivalent circuit? Which is, how do you obtain a model? So look at this. See this? How do we obtain a model for this? That is an AC equivalent circuit of this, in order to do our small signal AC analysis. How do we do that? How do we draw the diagram? And these are the steps to follow. Okay. So instead of reading or just stating all this, I won't do that now. I will do this, or I will say this out in the next video, which will be this. And while I talk about it, we are going to draw the model, the RE model. We might say that we are working with the RE model because it's more flexible and convenient to work with. So while I state this point in the next video, we are going to apply it here. So we are going to use that point to draw the RE model of this circuit. Note that it's a common emitter fixed bias configuration. Okay, so yeah, that will be all for this. This will be all for this video. Okay, so in the next video we obtain the AC equivalent of a network, which is the model of a network. So I'll see you in this video. Okay, that's in the next video. So yeah, like, share, subscribe, comment, and then yeah, so basically all we did in this video is introduce the concept of a model. I talked about transistor model and a few things to note, and then the two types of model being the hybrid and the RE model, and then how to obtain an equivalent circuit. We are going to do that in the next video. So I hope this was helpful in a way, and yeah, thanks a lot for watching, and bye for now.